This video demonstrates Dendrite, which enables data systems to easily adapt to changes in workload and system behavior. It is desirable for modern data systems to respond to fluctuations in client workloads. As an example, if the client workload suddenly increases demand, the data system's performance may degrade. To remedy such issues, administrators must detect these performance problems and reconfigure the system to fix them. In this case, the administrator remedies the load spike by distributing load among the main and replica databases, reducing contention. To reduce administrator burden, adaptive data system components are becoming popular. These components extract important features and metrics from the system, determine when system behavior has changed, and deploy an appropriate system adaptation to restore system behavior to normal. Implementing these components in popular systems is challenging because each system has different metrics, notions of important behavior changes, and varying techniques to remedy them. Our system, Dendrite, addresses these challenges by easily integrating with arbitrary data systems to provide adaptivity. Dendrite exploits built-in debug logging and system metrics to provide this functionality. In our load spike example, Dendrite uses database execution logs and aggregate system metrics. Using this information, Dendrite identifies how system behavior differs and determines which of these differences are important. Here, Dendrite determines that there is a significant increase in serialization failures, disk activity, and database worker processes. Dendrite matches these differences to user-defined functions and executes them to remedy the behavior differences. For example, Dendrite can contact a load balancer and change the routing to reduce the load spike contention. In this demonstration, we show how Dendrite automatically remedies a load spike in PostgreSQL. This top panel shows system behavior over time. The first circle is gold, which indicates that the behavior in this interval differs from the administrator configured expected behavior, or that of the previous interval. This is because PostgreSQL has just started and is warming up. Afterward, system behavior returns to normal, as indicated by the teal circles. Here, each circle corresponds to a 30-second window of system behavior. As the system executes, the interface updates to include the recent time window. Soon, we observe a change in system behavior. After one interval, Dendrite deploys a reaction rule as a remedy, shown in this top pop-up window. The left side of this window shows the largest behavior differences in terms of event proportion for the current interval compared to the expected behavior. We see that there is a large increase in serialization failures and disk activity associated with the load spike. The top right of the panel shows the user-defined reaction rule that Dendrite matched to this behavior difference. Specifically, the ratio of new PostgreSQL worker processes over active processes is 30%, or 30% of all running PostgreSQL worker processes started in this interval, which indicates a load spike. Therefore, Dendrite executes the shedLoad user-defined function. This function alleviates the load on the database by reducing the number of active client connections and restores normal performance. Dendrite supports arbitrary Python user-defined functions, so other behavior modifications can be encoded here as desired. To ensure that we are alerted to this behavior change in the future, let's register a new reaction rule, using the existing one as a template. We'll use the sendEmail UDF to send an email to the administrator. Now, let's investigate what happened in the first interval exhibiting a behavior difference. The top left panel shows the reaction rules that have been fired in response to the differences in this interval. The rule we discussed before appears here. The lower right panel shows how behavior differs in the current interval compared to the previous interval. We see a large increase in aggregate disk activity per operating system counters. Similarly, the largest difference in terms of event proportion are relation block reads, or page reads from disk. Consulting the left panel, which shows differences compared to the registered baseline, we observe similar differences: large increases in aggregate disk metrics, and a larger proportion of disk read events compared to baseline. The Processes button displays the new and active processes for the data system in this time interval. Dendrite identifies these processes using behavior fingerprinting. It compares the behavior it has captured for each process to registered representative models of Postgres processes. We will describe this technique in more detail after this scenario. We see that Dendrite has identified a large number of new PostgreSQL worker processes, which corresponds to the load spike. It is this difference in process behavior that matches the reaction rule and triggers the shed load functionality. Clicking on the subsequent time interval, we see that the reaction rule is now in the in-flight adaptations panel. This means that the rule was fired in the previous interval, but its effects are ongoing and have not yet restored behavior to normal. We can observe this effect in the below right panel, where we again see a large increase in disk activity. We also observe increases in proportions of serialization failures and lock contention. Similarly, we observe more disk activity compared to the expected behavior. We also see increases in proportion of serialization failures and page read events. As new information comes in, we observe that Dendrite has restored the system to normal behavior, as indicated by the teal circles. Clicking on a normal behavior interval, we observe that Dendrite has significantly reduced disk I/O through its reaction rules over the previous interval. Moreover, the Processes panel shows that Dendrite has reduced the number of active processes and thus restored normal behavior, as exhibited in the following time intervals. Sometime later, we experience another load spike. The pop-up window shows a large increase in serialization failures and disk I/O with respect to baseline. Accordingly, we see that Dendrite has deployed both the original shed load UDF and the new send email UDF that we registered. Checking the panels below, we observe the disk I/O increase associated with the load spike, along with an increase in lock contention. To confirm, we open the Processes tab and see a large number of new PostgreSQL worker processes. Shortly afterward, we again see the effects of Dendrite's reactions, as evidenced by the reduction in disk I/O. Let's take a step back and discuss how Dendrite provides this functionality. As mentioned earlier, Dendrite extracts system behavior from debug logging and system metrics. We'll start by discussing how Dendrite integrates with built-in debug logging. Data systems append to debug logs by making a log call in code with the appropriate log level and message. To integrate with Dendrite, we modify the logging library that handles these calls to first pass this information to Dendrite, which stores it in in-memory models. These models capture how the data system moves between logging events as a variable order Markov model. Afterward, the call is sent to the logging library as normal, thereby preserving the original logging behavior. Dendrite also encodes low-level resource metrics into these models. To obtain this information, Dendrite intercepts important libc calls. For example, if the data system makes a write call, that call is redirected to a custom implementation of write that tracks statistics like the number of bytes written. Dendrite associates these statistics with the events taking place before and after the write call so that administrators can determine the resource-intensive components of their system code. Afterwards, the write function is called as usual, preserving the original behavior. Dendrite also obtains aggregate metrics from the system using dstat. By combining all of this information together, Dendrite obtains a holistic picture of system behavior. Dendrite compares a time intervals model against that obtained from a previous interval, as well as a model registered by the administrator that represents ideal system behavior. To obtain such a model, an administrator can have Dendrite export a time intervals model when the system is performing well. The primary means Dendrite uses for these comparisons is differences in relative event proportion. For example, it considers if disk read events make up a larger proportion of events in one model than another. It ranks its outputted differences in this order. If the mean proportional difference exceeds a pre-configured threshold, we say the differences are significant, and Dendrite checks if there are matching reaction rules it can execute. By using event proportion, Dendrite is resilient to slight changes in overall event count during a given time interval. Dendrite also uses this technique to identify running data system processes. The combined time interval model is decomposed into that of individual processes and compared to administrator-registered models to identify which classes of processes are running. Doing so removes the need to rely on process and thread naming conventions. Administrators register reaction rules for Dendrite to execute when a targeted behavior change is observed. For example, an administrator may register a rule indicating that if the number of Postgres worker processes increases by 30% in one time interval, then the shed load user-defined function should be called, as in the first scenario. Dendrite matches these conditions against the observed system behavior differences and evaluates any matching rules. Note that rules may be arbitrary UDFs and therefore can be used to encode a large variety of responses. With this in mind, we will now further demonstrate Dendrite's utility by rectifying excess disk I/O due to auto-vacuuming and checkpointing in PostgreSQL. We start in the second time interval, where Dendrite has recognized a behavior change and responded accordingly. We see a large, disproportionate number of disk reads compared to the expected behavior. We also see that Dendrite has matched and evaluated the following reaction rule. Specifically, if the amount of data written in this interval is greater than 25 megabytes, and more than 2 megabytes of that is due to page flushing, the associated events in this rule, and the checkpointer is active, then dial back the frequency of checkpointing and auto-vacuum to reduce disk pressure. Consulting the first time interval, we can see that there is an overall increase in disk activity compared to expected, and a disproportionate increase in reads, which is likely due to the system starting up. Consulting the processes panel, we can see that Dendrite has identified and determined that the checkpointer and auto-vacuum launcher processes are running. Although Dendrite's reaction is deployed immediately, PostgreSQL checkpoints take a significant amount of time to complete, which is why the behavior continues to be different from expected over time. We see these effects in subsequent intervals. The reaction rule is ongoing. The checkpointer is still active, and there are a large number of disk writes compared to baseline. Clicking on the right bar in this graph shows which parts of the code are responsible for the disk writes using libc metrics. In particular, we observe that the code path between relation block write start and relation block write done are associated with a large proportion of the writes in this interval. We can use this interface to go back one event further to see the events that led to this code path, and note that it comes from buffer page flushes. Buffer page flushes are caused in this case by checkpointing in PostgreSQL, and hence the checkpointer is responsible for this I/O overhead. Eventually, the ongoing checkpoint completes, and Dendrite returns the system to its expected behavior. We observe that it has significantly reduced disk I/O so that it is comparable to the expected behavior, and that the checkpointer is no longer active. In doing so, it has significantly improved query performance. For more details on the Dendrite system, please see the associated paper.